We live in this world that's just incredibly interconnected. Everything from global finance to, say, insurance markets. But what if I told you there's a kind of hidden mathematical language that describes exactly how these things are connected, especially when things go really, really wrong? Well, in this explainer, we're going to pull back that curtain on a super powerful tool that does just that.
I mean, just think about that for a second. How do you predict a perfect storm? When a massive hurricane hits in the same year the stock market decides to tank. Or when two investments that seem totally separate suddenly both nosedive at the exact same time. How on earth do you even start to calculate the odds of that kind of catastrophic overlap? This isn't just some academic puzzle, right? This is a critical question for anyone who's managing risk.
So before we can get to the solution, we really have to get our heads around the problem itself. And the heart of the problem is trying to figure out the joint probability, the chances of multiple things happening at the same time. And, well, it's a lot trickier than you might think.
Okay, let's make this real. Imagine you're an insurance company. You've got a portfolio for home insurance and another one for car insurance. Now, you probably have a pretty good idea of the risk for each one on its own. But the real killer question is, what are the odds of a totally disastrous year for both portfolios in the same year? See, a single event, like a huge flood, could trigger an avalanche of claims in both categories. How do you possibly model that connection?
Now, the first tool that pretty much all of us would reach for is correlation. It's famous, it seems straightforward, but as we're about to see, when you're trying to understand these really complex connections, correlation has some pretty serious blind spots.
So what is correlation, anyway? At its core, it's just a single number, somewhere between -1 and +1. And it tells you how well two things move together, in a straight line. If it's +1, they're in perfect lockstep. If it's -1, they move in a perfect opposite way. And if it's 0, it means there's no linear relationship. And that word right there, linear, that's the whole catch.
And this slide just lays it out so perfectly. Look at the left side, a classic straight-line relationship. Correlation sees that, no problem, and it would give you a really high number. But now look at the right. I mean, come on, there is clearly a very strong, very obvious pattern happening there, right? But because it's not a straight line, Pearson's correlation might be close to 0. It would be completely blind to a relationship that's staring us right in the face. And in the real world of finance and insurance, things are almost never a simple straight line. So, if correlation isn't good enough, then what is? This brings us to a really elegant and, frankly, powerful idea. A totally different way of thinking about the problem, which is basically to break it apart.
What if, instead of trying to model this whole tangled mess at once, you could analyze each risk totally by itself, understand its own unique behavior, and then, as a completely separate step, you could pick from a menu of different recipes or glues that describe the exact way they're connected. This right here is the core insight that changes everything.
So here's how it works in practice. Step 1. You model your household insurance losses. You figure out their unique probability distribution. Step 2. You do the exact same thing for the car insurance losses. And then, step 3. This is the magic step. You select a mathematical function whose only job is to describe the dependency structure between them. And that special function? It has a name. It's a copula.
Okay, so we've given it a name. But what exactly is this thing we're calling a copula? Let's get a clear definition.
In the simplest terms, a copula is the glue. That's it. It's a function that takes the individual probabilities of each event and it spits out the combined joint probability. Its whole purpose in life is to isolate and describe the relationship itself, totally separate from the things it's connecting.
And this visualization really helps. On the left, you see you've got the individual probabilities of two totally separate events. The copula is that engine in the middle. It's the mathematical bridge that takes in those two distinct probabilities. And then, based on their specific dependency, it produces that single, joint probability of both of them happening together.
Now you might be thinking, okay, this whole idea of taking a tangled mess and neatly separating it, that sounds nice, but is it mathematically legit? Well, the answer is a huge yes. Way back in 1959, a mathematician named Sklar proved that this separation is always possible. Sklar's theorem is the solid bedrock that this entire field of modeling is built on. It's not just a clever trick, it's proven math.
So, why does all this matter? Why go through all this trouble? Well, this whole method of isolating the dependency, it has a superpower. It is incredibly good at modeling what happens in the extremes, not on your average Tuesday, but during a full-blown crisis.
And this brings us to a crucial concept called tail dependence. Basically, it's a way to measure how likely it is that if one thing experiences an extreme event, like a massive loss, the other thing will too. It's asking a simple question: do disasters tend to strike together? Your standard correlation is terrible at answering this, but copulas, they are designed for this very question.
And this quote from the source material just hits the nail on the head. In the real world, especially in finance and insurance, the data shows that things don't just fall apart randomly. They often fall apart together. A market crash doesn't just hit one stock, it tends to pull a whole lot of others down with it. This is exactly the kind of tail dependence we absolutely need to be able to model.
So here's the real game changer. Remember correlation? It just gives you one single number for the whole relationship. That's it. But with copulas, you actually get to choose from a whole family of different functions to model different kinds of connections. You can literally pick a copula that says, hey, these two things are mostly independent, but during a crash, they become intensely connected. That kind of flexibility is what makes them so incredibly powerful for managing risk.
So if you take just one thing away from all this, let it be what you see right here. The big idea behind copulas is to stop looking at a complex system as one giant tangled mess. Instead, you isolate the individual parts, you understand them deeply, and then you choose a specific tool, the copula, to act as the link that precisely describes how they're connected. It is a much more flexible, much more powerful lens for seeing and managing risk. And all of this leaves us with a final thought, doesn't it? The mathematical models we choose to use, they aren't just abstract exercises. They literally define how we see the world and the huge decisions we make based on that vision. Copulas show us that there are these deeper, more nuanced ways to understand connection. And it really makes you wonder, in a world that is so full of hidden dependencies, are we actually using the right tools to see the connections that truly matter?